All right. Hello, everybody. Welcome. So it's a pleasure to welcome our speaker today. It's Thomas Koberda from the University of Virginia, and he's going to tell us something about the first-order rigidity of homeomorphism groups of manifolds.
Great. Thank you, Ilya, for the introduction. Thank you, everyone, for coming. It's a great pleasure to get to speak here again at the New York Group Theory Seminar. Yes, so I'll be talking about first-order rigidity of homeomorphism groups of manifolds. Right? So this is joint work with Sang-Hyun Kim and Javier de la Nuez Gonzalez. We're both at Kias. Since we haven't posted a preprint yet on the archive, I've given a link here, so the preprint's on my webpage, and there's also a Dropbox link here. All right. So to get started, right? So the basic question that I'd like to consider is, so to what degree does homeo of a manifold M determine M? Okay, so here M, I'll just always take this to be, so M is a manifold. And in this talk, I'll always assume that it's connected. And also, for the sake of not having to repeat this over and over, I'll assume that it's compact. Okay. So, right, there's the question of to what degree does it determine M, and also how does it do so? Okay. So maybe to motivate the discussion, I'll start with a classical theorem from the 1960s. Is a theorem due to Whittaker. Okay, so Whittaker says that if M and N are compact manifolds, and if you let phi be a homeomorphism, phi an isomorphism between the homeomorphism group of M and the homeomorphism group of N, then this implies that M and N are homeomorphic. And in fact, if we can name this homeomorphism between M and N by psi, and we have that phi of F is given by psi composed with F composed with psi inverse. So it's so the isomorphism between the homeomorphism groups determines the homeomorphism between the underlying manifolds, and the isomorphism is given by this very specific type of map, just conjugation. Okay, so that's a very sort of satisfying thing, right? One can also generalize this to other kinds of homeomorphism groups and diffeomorphism groups that can be associated to a manifold. You know, there's work of Takens combined with stuff by Bochner and Montgomery. Sometimes there's work that's attributed to Filipkiewicz that says if M and N are smooth, and if you have an isomorphism between, say, their diffeomorphism groups like this, Then this implies that K is equal to L, and M and N are CK diffeomorphic. And moreover, you have the same conclusion that the isomorphism between the groups is induced by conjugation by a CK diffeomorphism. Okay, well, that's great. But I mean, I like to think about, you know, these homeomorphism and diffeomorphism groups from a much more hands-on perspective. And then if you say something like, okay, this homeomorphism group is isomorphic to this other homeomorphism group, that I find that to be a rather unwieldy piece of information. I mean, these homeomorphism groups and diffeomorphism groups of manifolds are incredibly big, and I think we all know that sort of abstractly. But I mean, they're just to talk about an isomorphism between two homeomorphism groups is such a refined and such a remote piece of data that I don't really know what to do with it or how to even approach describing such a thing. And so what I like to think about instead are sort of more finitary ways of understanding how the homeomorphism group of one manifold relates to the homeomorphism group of another manifold. So what I'll prefer is a finitary approach via first order logic. And so maybe I can just spoil the punchline immediately. So I'll just state the main theorem. So the main theorem is that as follows. So let M be closed and connected. So then there is a sentence phi sub M in the language of group theory. So that is to say, where you only have access to the binary multiplication and the distinguished identity element within the language, such that if N is any compact manifold, so not necessarily closed and not necessarily even connected, and if homeo of N models this sentence, then M is automatically homeomorphic to N. Okay. So there is, in other words, a sentence in the language of group theory that the homeomorphism group of a manifold can say about itself, which is satisfied precisely by the homeomorphism group of another manifold precisely when those two are homeomorphic to each other. Okay. So this is, I think, the easiest and straightforward, most straightforward way of stating the main result. I'll say some addenda here, which ways that this is actually slightly more general. So right, so we can assume, so we need only assume that homeo 0 of n models phi sub m, which is to say that the group of homeomorphisms isotopic to the identity in n. You can pass to that subgroup, and as long as that subgroup models this sentence, then that is enough already. Okay. And moreover, one can put some further restrictions on what the homeomorphism groups are. So if m and mu and n nu are manifolds as above, let's just say that m is closed and connected, and n is compact but otherwise arbitrary, and these mu and nu are what we call Oxtubby Ulam measures. So what these are Borel probability measures, which give the measure 0 to the boundary. Then you can consider these groups of homeomorphisms of m and of n, which preserve the measures mu and nu respectively. Okay. So we can formulate so that there exists a sentence psi sub mu, again in the language of groups, such that if the group of homeomorphisms isotopic to the identity preserving nu inside of n models psi sub m, then m and n are homeomorphic to each other. Great. So that's the main result. Let me just say something about history a little bit. So I found out when I was working on this theorem with my co-authors that this particular theorem was claimed already in some generality by Rubin. So this is Matatyahu Rubin, who did a lot of work on reconstructing spaces from their automorphism groups. So in a paper from 1988, maybe it was 1989, I can't remember right now. So he claims that if M and N are arbitrary manifolds, then if the homeomorphism groups of M and N are elementarily equivalent, then M and N are homeomorphic as manifolds. And he says that this is assuming V is equal to L. Okay, so V is equal to L this is a certain assumption about set theory that he's using. So this is just so V is the cumulative hierarchy of set theory, the von Neumann universe, and L is the Gödel constructible universe. basically saying that all sets in the cumulative hierarchy are constructible. And so he says that if you assume this, then you can prove for arbitrary manifolds that elementary equivalence of homeomorphism groups is equivalent to homeomorphism of the underlying manifolds. I have no idea what the assuming Gödel constructibility could possibly have to do with this. Yeah, so maybe it has something to do with the case of non-compact manifolds, which we found is a bit of a viper's nest. So that's why we restricted our considerations to compact manifolds. And I'll just remark that so the way that I'm announcing the result and the way that it's written up in the preprint that I advertised at the beginning, we assume that M is closed, but I'll just say that I'll say with some work in progress is that the same result is true when the boundary of M is non-empty, right? So all for arbitrary compact manifolds. So the existence of a boundary complicates matters pretty substantially. So we're still working out the details of that a little
Thomas,
bit.
just
Yes.
one comment. Basically, what you're proving, it's called quasi-finite axiomatizability, right? QFA, that there is a finite number of sentences like which determines the isomorphism type.
Yeah, I think it's actually just one.
But finite number is equivalent to one usually.
Yes,
like
yes,
it's
that's right.
because their result it's sort of first order rigidity result, right? Because usually they say that something is first order rigid if like the same elementary theory like provides isomorphism. When you prove more, you prove this is what's called quasi-finite axiomatizability.
Right. Yes, that's
just a comment. Yeah.
Yeah, thank you. Yes, that's true, right? So, yeah, we are identifying a particular sentence, which in principle could be written down, but I doubt that it could practically be written down. I'll sketch some of the ideas that go into the proof. I think it's even for something like the interval or the circle, it's not entirely obvious that this is something practical to write down. But yes, that is correct. It is stronger, strictly speaking, than first order rigidity. Thank you. Okay, right. So that's an overview of what we proved, and to sort of give an indication again of a bit of why I care about this, right? So I mentioned at the beginning that that you have these classical theorems of Whittaker, which say that isomorphisms between homeomorphism groups imply homeomorphism of the underlying manifolds, and same if you pass to diffeomorphism groups. And so and I said that I wanted finitary ways of distinguishing between homeomorphism types of manifolds that only use groups acting on them. So here's a question which I have no idea how to solve in general, but which I think maybe these results that I'm talking about here might be a first step. Okay, so can you find, so maybe I'll say this slightly differently. So for each manifold, so here compact manifold M, does there exist a finitely generated group, maybe G sub M, such that G sub M acts by homeomorphisms of M faithfully, and G sub M does not embed into homeo of N for M, not homeomorphic to N. So to use, so basically to find finitely generated groups, which simply by virtue of their algebraic structure can be used to distinguish between homeomorphism types of manifolds. And another question is, the same.
I'm sorry, Thomas.
Mhm.
Do you really mean what you asked here? Because I don't think that the way you asked this question, it could possibly have a positive answer, right?
So what do you mean?
I mean,
Maybe after maybe restricting the dimension or something.
yeah,
Okay,
that's the kind of thing that I
so
meant.
maybe.
I mean, you probably have to put some additional restrictions here to rule out some, some obvious counterexamples, such as products or just adding some connected components.
Yeah. Okay. So I'll just write with some provisos. So with whatever. Yes. Thank you. With whatever sort of assumptions that one would need to avoid sort of fairly straightforward to construct counterexamples. And then one can ask the same question for diffeomorphisms. I mean, so one thing that I spent some time in my life thinking about was distinguishing even between like different groups of different regularities acting on the interval and on the circle. So for instance, so this is a theorem of Kim and myself that says that for all k in N, there exists a finitely generated group, maybe call it gamma k, such that gamma embeds into diff k of the interval, and you can replace the interval by S1, you get the same conclusion. But any homomorphism from gamma k to diff L of I, for here L greater than k, has abelian image. So here gamma k is supposed to have is not abelian to begin with. So you have so gamma k is some complicated group which has like maybe a simple commutator subgroup, and it acts faithfully by CK diffeomorphisms on your favorite one manifold, so the interval or the circle, but any smoother action factors through an abelian quotient. Right. So I mean, I'd like to be able to find groups like this for manifolds in dimension 2 and higher, and at present I have no real idea of how to do that. But in any case, this first order rigidity of homeomorphism groups may be a good first step. Okay, so with that, maybe I'll say a few words about how one might approach a problem like this. So some indications of the proof. So basically what one needs to show is that the homeomorphism group can be used to recover enough information about the underlying manifold to determine its homeomorphism type. Okay, so the first thing that one would need is some way to know in sort of intrinsically when two manifolds are homeomorphic to each other or not. So the main engine that in the end makes the entire argument work is a deep result of Cheeger and Kister. Okay, so if you look at this paper that they wrote, this is from the 1970s, right? So what they were trying to prove is that if you look at compact topological manifolds, so they prove that they come in countably many homeomorphism types. Okay, so that by itself is sort of not is not helpful for trying to prove first order rigidity of homeomorphism groups of manifolds. But the sort of inner workings of their proof, which is remarkably simple, are sort of very valuable in trying to understand the.
Sorry, say it again. What did they prove? They proved that there are countably many homeomorphism types for compact.
Yeah. So their theorem said that that if you look at the homeomorphism types of compact topological manifolds, that this set is countable.
If one believes that everything can be triangulated, then this is probably, I mean, immediate.
But are there issues in 4 dimensions?
With being able to triangulate manifolds?
Yeah.
Yeah. Oh, yeah.
Yeah. So I think that this is a non-trivial.
Oh, okay. Yes. Sorry.
Non-trivial fact.
So I was thinking about small dimensions. Yeah, you're right.
No. I mean, this is a good point. Yeah, and in the smooth category, you have arguments like, you know, looking at like Kobordism and, you know, finitely many kinds of, you know, finitely many types of singularities of some Morse function, and so it's, if you have more structure, then it's easier. But this is a completely naked manifold. It only has topological structure. It's only locally Euclidean, and that's all. Okay, so the output of this theorem is not particularly important for us, but what they proved is the following. So they start with a manifold M. Okay. You can pretend that it's closed if you want to make this slightly easier at first pass, right? And you cover M by K many balls. Okay, say B1 to BK. Okay, and then you consider an arbitrary embedding of M into R to the L for some L. Okay. And so what this embedding tells you is what it gives you in particular is a map, right? So if you call this this map, say, I don't know, iota, and this cover collectively is U, you get some map F depending on iota and U from just a ball in R to whatever dimension M is into R to the KL just by restricting the embedding to each of the balls separately. Okay, it's just the product map. Okay. So an important technical lemma in this Cheeger-Kister paper, which I'm stating slightly sloppily, but it's the thrust of it is I think it comes out in the way that I'll say it, is that so if M and N are covered by K balls and have the same dimension, so then we embed both in RL by say these maps, I'll call them iota sub M and iota sub N. So there exists an epsilon which depends on U and on M, so that if you look at the L infinity distance between F iota sub M U, maybe the cover of U that you get, of M that you get by K balls, and you compare it to the corresponding embedding of the ball into RKL that you get, so that whenever these are close enough, this implies that M and N are homeomorphic to each other. Okay. So this is a lemma that is sort of deep inside of this argument of Cheeger and Kister, and gives you sort of a way of certifying that two manifolds are homeomorphic to each other just by looking at certain functions that are defined on a ball with values in some Euclidean space. Okay, great. So what does this do? Well, okay, so this gives us a hook into trying to prove that the first order theory, at least of the homeomorphism type of M, sorry, the homeomorphism group of M determines the homeomorphism type of M. The challenge then is to be able to produce all these pieces that make up this lemma, namely, how do you say things like M is, or a manifold N is covered by K balls, and also like how do you even express that N has a particular dimension, and then how do you talk about balls anyway, right? So I mean, like if I give you, if all you have is the homeomorphism group, how do you know what the balls in M are? And by ball, I really do mean like an embedded copy of a metric ball in some Euclidean space. And then how do you talk about continuous functions? So how do you find all these things? Well, it turns out that it is all possible. And so once you interpret all these things in a way that's uniform in M, then you're basically done by this lemma. So as long as you can write down formulae which don't depend on the underlying manifold, which are just formulae that live in the language of group theory, and which for different homeomorphism groups will interpret the same things in a faithful way, then you will be able to express exactly when, for a given embedding of a ball in R to the KL coming from a covering of M by K balls, then N also admits such a cover, which is close to that embedding, and so N has to be homeomorphic to M. Okay. So how might one even begin? Let me just summarize what I just said. We need to interpret the machinery of the lemma in the homeomorphism group. Okay. So the basic thing that the first step that one does is one needs to interpret things that are called action structures. So this is stuff that was known already to Rubin, and he works with a lot of with this through in a lot of his papers that look at especially actions of homeomorphism groups on manifolds. So basically the homeomorphism group of M interprets the Boolean algebra. Boolean, sorry, let's see. The Boolean algebra of regular open sets on M. Okay, so so what are the regular open sets? Okay, so so first of all, these are open sets. Okay, and an open set is called regular if it's equal to the interior of its closure. So these are sort of natural things to work with if you like sort of things that are well behaved under Boolean operations, because like if you have a regular open set, then you have a natural notion of a complement, because you can take the literal complement and then take the interior of it, and you get another regular open set. Okay, but if you do that with if you just use open sets and play that same game, you end up getting if you take the complement of the complement, that's not an involutive operation. So if you try to sort of build a Boolean algebra with just regular open sets, then with just open sets, then you end up getting a hating algebra instead, and not a Boolean algebra. So it's sort of like intuitionistic logic instead of classical logic. Anyway, so what is this? So basically, what you do is you go from G, and you associate what's called the extended support of G. Okay, so this is equal to the interior of the closure of the set of P, such that GP is not equal to P. Okay, so the thing in the curly brackets is the classical open support, and then the closure is what's oftentimes called the closed support, and then the interior of that is what we call the extended support of G. Okay, and so to interpret the extended support of a homeomorphism, that just amounts to putting a certain definable equivalence relation on homeomorphisms, which is I won't spell out, but the point is that the homeomorphism group knows what the regular open sets in the manifold are in a way that is not dependent on the particular manifold under consideration. So the formulae defining that equivalence relation are uniform among manifolds. Okay, so then when you consider groups, this is the group of homeomorphisms acting on the manifold, you may as well assume that you have access to the regular open sets on M. It is true, by the way, that every regular open set is the extended support of some homeomorphism, and so therefore you do actually get this full Boolean algebra. So that's the first step, and that's something that's, I think, well known from the work of Rubin. So one can only do so much with regular open sets. One finds quickly that one's hands are tied if one tries to do sort of things that are natural in topology. For example, even things like talking about points, like how do you nail down a point? Like, or how do you express that an open set is a ball? Like, you may be like, oh, well, you know, let's say that U is an open set, and then W is my favorite regular open set. If I can take some homeomorphism that sends U into the interior of W, okay, so that's, I mean, that can only be true if, so that will be true in particular if if U is homeomorphic to a ball, fine, but it doesn't characterize balls at all. I mean, if the regular open set you started with was contained inside of a ball, then it would also have the property that it could be sent into your favorite regular open set by some homeomorphism. Okay, so but on the other hand, that set U could have holes in it. It could be, you know, something quite miserable. So what can you do with this? Well, the next thing that one has to do is one has to interpret second order arithmetic. Okay, so before one can do this, one has to develop some machinery for dealing with regular open sets. Okay, so for example, you need to be able to talk about things like connectedness, having the same the number of components being equal between two regular open sets. If you have like a regular open set U and regular open set V, you need to be able to say that these have the same number of components, for example. And also something that's somehow very basic when we think about topology, at least from sort of the second order logic point of view, but which is significantly harder if you want to say just in first order language, is distinguishing between infinitely many and finitely many components. So in particular, you do have formulae which are satisfied by a regular open set if and only if they have finitely many connected components. Okay, so that's that takes some work to prove. Okay. So then one can interpret arithmetic. Okay, so one starts with first order arithmetic. So you just have to, you first start by defining, you build, you know, some collection of regular open sets, X inside of N, and then you, instead of the regular open sets of M by some definable properties, which I won't get into them. I mean, this is all written up in our preprint if someone is interested in the details, but saying all the details now will be sort of not very enlightening and will take too much time. And then one imposes some equivalence relation on X mod E, which is sort of in canonical bijection with N. Okay, and because you're able to count connected components of regular open sets, you can interpret addition, and you can interpret multiplication, you can interpret the order, you can interpret the successor. And then because you can also pass to subsets when you deal with regular open sets, you can interpret more than just first order arithmetic. You can interpret all subsets of N. And so that allows you to interpret second order arithmetic. So once we get second order arithmetic, that's really the same as in being able to interpret analysis. So in a uniform way, the homeomorphism group of a manifold, it knows about Rn, it knows about continuity, it knows about anything that you can formulate in first order analysis, okay, in the language of ordered rings. So then the next thing that we needed to do is to interpret points. Okay, so this, when we were originally thinking about this, we thought that we could get away with not interpreting the points at all, but in the end, this ended up being a centrally important part of the entire argument. I mean, so if you look at regular open sets and you want to say, I want to pick out a particular point on the manifold. So the natural thing that you might consider doing is you take a sequence of nested, of nested regular open sets that they get smaller and smaller. Maybe each one is relatively compact in the previous, right? And they shrink down to some point, or at least some compact set, and then maybe you put some more conditions on it to make sure that the intersection is exactly one point. Rubin does this in his work too. He calls these, good ultrafilters, which are the ones that isolate particular points. Right? But I mean, you can't really quantify over. You can't really build these ultrafilters inside of regular open sets with first order language, or not in an obvious way. Even if you have interpreted analysis already. So one can sort of play a similar game, right? So the way we ended up interpreting individual points is you interpret them by some sequences, so not sequences, a particular regular open set, right? So each point is encoded by a particular open set. Up to some equivalence relation, all of which are definable. And so the way we built these regular open sets, so the way to imagine is that you have a point here, okay, and we had so these red rings that I'm drawing you should think of them as thickened. So they're actually like regular open sets, and they're shrinking and encircling P. Okay. So you may think that I'm cheating somehow, that I'm appealing to second order logic in some way, but I'm not, right? So the thing that one has to express about the components of this regular open set is, first of all, that there are infinitely many components. Okay, that's fine because of something that I set up here, right? So you know when a regular open set has infinitely many components or not. And what's more is that they are nested, so they cut they cut the manifold into two pieces, each of them. Okay, so that's something that we can express using, well, the language of action structures. So that's fine, and that exactly one piece of the complement of any one of these regular open sets contains infinitely many components of the original thing. So that's something that we can also do, and that there's exactly one component which, when you cut open, that you have k components on one side and infinitely many in the other. Okay, so that the order type of these sets shrinking down to a point is sort of the one that you expect. It's like the omega order type. Okay. And then the last thing you need to do is then you need to make sure that you converge to a unique point, which basically means that if you have two neighborhoods of points, then you have to make sure that one of them is eventually contained in the outer part of these red rings that are encircling the point. So that is a specific way that one can encode particular points without resorting to ultrafilters. Okay. And so then the last thing that one needs to do is to interpret balls. Inside of M. Okay. So for this, first of all, we needed to be able to interpret the dimension of a manifold. So once we knew what points were, then we could talk about when a particular collection of regular open sets covers, or at least find if you knew how many components, if you know how many sets there were in that collection, so that you could actually quantify over it. You can talk, if you know what points are, then you can talk about covering. Okay, and it's possible to encode enough dimension theory to detect the dimension of M. Okay, so that's possible. Okay, and then now that we have analysis and we have points and we know what the dimension is, then basically what you can do is you can interpret what it means for there to be a point here P in the manifold and a locally defined action by Rn to maybe I wrote this really poorly. So let me say you have P contained in U and some and a free action of Rn on P supported in U. Okay, and so what this gives us is a way to talk about particular balls, namely the images of Rn under this action. Okay, and these, if you do a little bit more work, then you actually can talk about a parametrization of this ball. So you can, I mean, you know what the points in Rn are because you've interpreted analysis, and the parametrization sends the origin in Rn to the point P, and then every point in some ball containing P is just parameterized by a particular point inside of Rn. And so once you have all of that, then you have all the pieces that are needed to implement this lemma of Cheeger-Kister. Okay. So we know about, I mean, the analysis lets you talk about functions, okay, and their continuity. And if you combine arithmetic with the interpretation of points, which also required arithmetic in a slightly more subtle way, then we can talk about balls sitting on a manifold. Right? We know when they have dimensions, so we can talk about them being covered, two manifolds being covered by K balls. And we can talk about the existence of these functions, which then a function from defined on a ball with values in RL, okay, has to simply satisfy some compatibility conditions to make sure that it arises from a covering of the manifold. But all these things are somehow first order expressible inside of the homeomorphism group of M now. And so that's all we need. So that's why the main theorem follows. So I think I'll stop here.
All right, thank you very much. Thank you, Thomas. That was very interesting. Any questions for the speaker? You're welcome to ask them now. So I had some questions along the way. Remember what
sure.
they are. So somehow it seems to be that being able to interpret second order arithmetic, right, is crucial. So what exactly allows you to do that? You know, so how is it that it's not just the first order arithmetic, but the second order arithmetic can be seen inside this homeomorphism groups? You know, so what's
right,
the main there?
So because you have right, so so n becomes is then in bijection with some equivalence class of regular open sets. Okay, and the components of U are so you have K here is in N is then sent to a particular component U sub K in pi 0 of U. Okay, so then the inside of P of N, the power set of N, the element relation, so is an element of relation, and the is a subset of relation are simply so element of and subset of are interpreted simply as contained in as a connected component. Inside of this particular regular open set U, which represents some interpretation of N. Okay. So because you can, because you can talk about, you know, this particular subset of this regular open set consists of components of this larger one. That's I mean, if this regular open set was interpreting N, this allows you to say that this is a subset of N, or interpreted as a subset of N. So that's the main point there.
I see. And so why was it important to work with regular open sets as opposed to open sets? You know, so
right, it's because right. So let me just say one more thing, because to talk about like why it's legitimate to talk about second order arithmetic and not just first order arithmetic. So like if I wanted to quantify over, say, like for all X subset of N, right? So how do I talk about this in the language of regular open sets? So I'm just going to drop the equivalence class. Everything is up to this some sort of equivalence relation, which is definable. Then I'm simply talking about saying, well, for all V such that you know, V hat in pi 0 of V implies V hat is in pi 0 of U. Okay, so these are then exactly the same. Okay. So why did we want to why did we look at regular open sets as opposed to just open sets? Well, the basic reason is that we sort of use the Boolean operations a lot, right? So in regular open sets you have you have intersection, you have the join, and you have the perp, right? So intersection is what you think it is, then the join is that if you join V is the interior of the closure of U union V, right? And then perp is U perp is the interior of M minus U, right? So if U is not regular, then it's then U perp is may properly contain U. This is possible,
Yes,
right?
see.
So it's not involutive like that.
Mhm.
And so in some sense, so one thing is that if you ask me to show that every open set is the support of some homeomorphism, that's also significantly harder than showing that every regular open set is the extended support of some homeomorphism.
Is it even true that every open set?
I wouldn't put money on it. Yeah, especially in maybe in like low dimensions, yes, but once you get to 4 dimensions, I wouldn't put money on it.
But I don't know. I'm not even sure that it's true in low dimensions, right? There may be some stupid counterexamples like the complement of a point, right? You know, so.
Yeah, I mean, you may have.
Wait a second. No, that's not what I'm thinking about. So sorry. Still, I'm not sure. Yeah, that there could be some strange behavior. So okay.
Right. So in any case, if you work with regular open sets, then you can interpret the full Boolean algebra of regular open sets inside of homeomorphisms of M. That's one of the main reasons that you want to work with it, and then it's well behaved under Boolean operations.
Okay, very good. All right. Any other questions for Thomas? All right. If not, then let us thank Thomas again. Thank you.
Thank you so much.
So I'll stop the recording in a moment.
Perfect.